So our next speaker is going to talk about insights into ferroelectricity with hafnium zirconate thin films, a new ferroelectric phase.
Good morning. Thank you for the introduction. My name is Pavan. I come from SPMS lab at Central Supélec in Paris. I work with Brahim, who's here in the audience. And this work, in fact, it's a pleasure to be speaking in front of such a distinguished audience, and I thank the organizers for this opportunity. This work is, in fact, a collaboration between our own lab, Beatrice Noida's lab at the University of Groningen. Yingfen is a student who is actively involved in this. And Jorge and Edje from Luxembourg Institute of Science and Technology doing a lot of computation for this. And of course, Philip and Sylvia, who do a lot of nanofabrication to make devices for this work. And both of them are also from C2N in Paris. So let's get started. First things first, why study ferroelectricity in hafnia? And I don't think we have, I need to motivate this crowd here, but I'll anyway do it. From the perspective of everyday electronic devices have like billions of transistors in them. And these transistors switch from an off state to an on state. And ideally, you would like a transistor characteristic to be something like this, where shown in the red, where in the off state you have zero current, and in the on state you have some finite current, and the switching happens very sharp. But ideality is not reality, and in reality we have MOSFETs which kind of leisurely go up from the off state to on state. The slope of switching is what is characterized by subthreshold slope or subthreshold swing. And that is given by this expression. And if you look at this expression, we see that just for conventional metal oxides, this number cannot be made less than 60 millivolt per decade, because this 1 plus some positive number is always less than 1. Is always greater than 1. So the idea, and so if you operate these transistors just below the threshold voltage and above the threshold voltage, in the off state you do have some leakage current. And so when we have devices in off state, they are leaking. So there is power loss for devices in the off state. And if we look at how the gate, and this is the so-called subthreshold leakage, and the power losses because of this subthreshold leakage actually intensify as the gate length decreases, as we keep miniaturizing devices. So this is bad, but fortunately we have a solution for that, which is try to make this quantity negative, use a negative capacitance as a gate oxide, and it's well known, so instead of MOSFET, we'll be using ferroelectric FET or a negative capacitance FET, and negative capacitance has been demonstrated in these ferroelectric materials by several groups in the recent past. So what's the delay? Why not use ferroelectrics already in microelectronic ferroelectric FETs? The problem is a well-known silicon compatibility issue with well-known ferroelectrics such as PZT and SBT. And furthermore, as you scale the gate stacks down, these ferroelectric materials, they lose their ferroelectricity because of depolarization fields. So a solution to this is perhaps to have let's call it a magic material, which has a robust nano ferroelectricity and which is also silicon compatible. And does that material exist? Yes, of course. There is hafnia, and it has been discovered, ferroelectricity in hafnia-based materials has been discovered in 2011 by this group in Dresden. So a quick introduction to basic structural details about hafnia, and which is very isostructural with zirconia, because hafnium and zirconium have almost the same size for a given coordination and charge. So hafnia exists in the bulk phase, exists in this bulk monoclinic phase, where hafnium is coordinated with 7, has a coordination number of 7, so surrounded by 7 oxygens in such a polyhedron. And the more well-known phase is the T phase, which is the high temperature phase and high pressure phase. However, this T phase could be stabilized by doping hafnium or zirconium with yttrium, magnesium, and these yttria stabilized zirconia, magnesia stabilized zirconia are like blockbuster materials for solid ion conductors. So these are very well studied. However, the problem with these two phases is both of them are nonpolar. So both of them are useless for ferroelectric applications. The saving grace is the existence of an orthorhombic phase. And this is what is reported to be ferroelectric, or what is assumed to be ferroelectric in most of the recent works in hafnia-based materials, ferroelectricity. So this phase was first reported in 1990s in zirconia as a bridge phase between the M and the T phases, but during the phase transformation, but there are no ferroelectric measurements until 2011. So since 2011, in fact, now it's a joke that you take any hafnia, any crystalline hafnia below 10 nanometers or something, it would become, and dope it with anything, it would become ferroelectric. So there have been several demonstrations based on different techniques and with different dopants. Insights, as always, come from theory as to what stabilizes this polar orthorhombic phase. And here, for instance, in this paper from in this paper from Munich, we have, they consider surface energy of these small nanoparticles to be a stabilizing factor for this polar orthorhombic phase. And then they, in fact, determine, for example, this red curve gives the energy stability of the ferroelectric phase, and it is stable in certain, say, size ranges, depending on the composition of the material that they're looking at. Similarly, this group from University of Connecticut, they have applied they suggest that while going, you could go to a polar orthorhombic phase by applying biaxial compression as well as electric field. So it looks like there are many pathways to get to this ferroelectric phase. However, the problem is that most of these films are polycrystalline, polyphase, so it's difficult to decouple individual effects experimentally and understand what the effect of each factor is on the ferroelectric, on stabilization of ferroelectric phases. So our strategy has been to, ideally, to design clean experiments where we study the effect of strain by changing the substrates. We study the effect of doping, specifically by choosing the hafnia-zirconia system, because zirconium has the same exact size as hafnium. So putting in zirconium in hafnium positions doesn't induce any internal strains, unlike, say, yttrium or lanthanum or some other ions. And also, we can study the effect of point defects by varying, in this experimental setup, by varying the oxygen partial pressure, for example. But what I'll show you in this talk is just one substrate, which is STO with LSMO as a back electrode, one composition, which is 50-50 of hafnium and zirconium, and the conditions optimized for growth of these films. So the stack looks something like this. It looks nice. But if you have a keen eyesight, you could recognize that at the interface of LSMO and SZO, something strange is happening, or something weird is going on. We will come back to this. But however, when you put another symmetric electrode and then measure the polarization electric field hysteresis, you do PV hysteresis, you do in fact see that for films which are thinner, 5 nanometer films, we measure a higher saturation polarization of around 35 microcoulomb per centimeter square compared to the thicker films. So this is true. Thinner it gets, the smaller the size gets, the better is the PV hysteresis. There is some new kind of ferroelectricity, or different from what happens in conventional materials. And so to understand that, we did structural characterization using both XRD as well as electron microscopy. So here I show a theta 2 theta XRD plots. as a function of the film thickness. So this is a busy graph, but I want you to note a couple of things. One is the literature value of the orthorhombic 111 is here. Whereas what we see in films which are boxed here, they are the ferroelectric films. The rest of them are not ferroelectric. So beyond this thickness, it is not ferroelectric. Is a lattice parameter which is larger than what is reported in literature, and also larger than what is in the in thicker films. So our ferroelectric films seem to have a longer out-of-plane parameter, which could be coming because of compression in plane. Okay, so you can do some pole figure analysis around this 111 peak, and then see that this corresponds to a domain structure. So of 4 different domains, which are rotated 90 degrees with respect to each other. Plane view TEM also says the exact same thing, TEM diffraction. So I circle the spots here in yellow, coming from 2 sets of domains, and in blue coming from two other sets of domains. And also we see a clear orientational relationship between the substrate and the film. Okay, so very quickly, because I don't have much time now, we do also cross-sectional stem measurements along by making cross-sections. So this is the plan view along this direction, along along several directions to get insights into what's happening. In thinner films, we do see a domain structure. Here I'm showing 180-degree domains. And in thicker films, we in fact see the evolution of not just 111 out of plane, but domains with 001, which is out of plane. And this is perhaps the reason why the polarization of this is less than the polarization of thinner films. So if we calculate what the d-spacings are, the d-spacings of 111 is different from 11-1, and this suggests, this is indicative of the fact that we don't have conventionally reported polar orthorhombic phase. In orthorhombic phase, these are supposed to be the same things. Same thing if you analyze the 001 domain, you do find some spots which are forbidden in a PCA21 orthorhombic phase. What phase is this? To do that, you go to the synchrotron, go back to this pole figure, analyze, let's say, all these spots, theta 2 theta scans around these spots. And here let's concentrate on one particular domain. Here we clearly see that there is a 3-to-1 multiplicity for the 111 peaks. And this is a clear indication that what we have is a rhombohedral phase, which has not been reported, which has been reported, but not in the context of ferroelectricity, and which is what excited our theorist, Jorge. So he did find a couple of rhombohedral polymorphs, which can be stabilized under strain using first principles calculations. And the polarizations of the more stable phases are like 15 microcoulomb per centimeter square. Actually less than what we measure experimentally. So this is one of the cases where theory is predicting lower numbers than what we are seeing experimentally. Okay, so as you keep increasing the thickness, this picture shows a gradual evolution to the M phase. Okay, so finally, let me talk about the interface. So the interface, these are the chemical maps, and we see that at the interface, we have a different phase of HZO itself, interface between LSMO and HZO. We have a different phase of HZO itself, and that is in fact a tetragonal phase, a T phase, which grows in the 001 direction, but it is completely epitaxially strained with respect to the substrate. So there is an 8% tensile strain T phase, which extends for 2 to 3 monolayers. Okay, so, and this is, so, okay, what is happening, right? So we do have LSMO STO. So here I'll show a very hand-waving cartoon. So I will select an in-plane parameter, which is convenient for me. So this is the 110 in-plane parameter of the LSMO STO, on which we grow a T phase. Initially, a T phase is formed for 2 to 3 monolayers, after which the system wants to relax strain. So once it relaxes, once there is strain relaxation, the next material or the incoming material should should have a lesser in-plane parameter compared to this strained T phase. But there is a substrate constraint. So the way the system accommodates this is by rotating the crystals from 001 to 111. And when you rotate it, you still have a higher, say, relevant parameter. So what we need to do now is to apply compression, some kind of compression. And in fact, this is well known in the literature of zirconia. And what happens in PLD, for instance, is there is in situ crystallization, so we have the formation of nanoparticles. That is one source of compression or compressive stress. And then the second one is the substrate constraint. So using these two, we actually compress this cubic or tetragonal phase into a rhombohedral phase. What we have is an R phase with a polarization, which is along a well-oriented R phase with a polarization which is out of plane. Okay, so the strain is accommodated by polar rhombohedral phase and domain formation, which is a standard trick to accommodate strain. And finally, this is me being patriotic. I come from India. In fact, this is the only flag where there's a wheel, which can be used to rotate crystals. And if you look at this, he's actually pointing out the direction of polarization. Okay, so I just want to point out that we submitted this paper recently, but it's available on arXiv. So if you're interested, you can take a look at this. Thank you very much.
We have time for some questions.
Just a comment to add in onto this. Another reason for using hafnium, of course, is that any sort of memory device based on ferroelectric hafnium dioxide will have write speeds which are orders of magnitude better than, for example, flash memories. And of course, there's very low power consumption. And then, as you said, I mean, this is really a comment, but the important point is that this is CMOS compatible. Yeah. So that it can go into production lines. There is no major issue on pollution or contamination, whatever. It's proven.
Sure,
so
sure.
Industry is interested.
So I was just taking one motivation, which is the FETs, but of course there is memory application. Yeah, so, sure, I agree with your comments.
Something known about critical temperature in such film?
Not in our work, but yes, it is known to be around 450 degrees Celsius or something.
Did you have to cycle the films to see the wake-up effect?
No, that's one advantage that I didn't mention here. In ALD-grown films, etc., which are in a different phase, clearly you have to cycle it. I showed you that curve where you have to apply electric field and then biaxial strain.
So these were virgin.
These are as prepared ferroelectric. You don't have to cycle anything.
Anything else? So I have a question. Sorry, go ahead.
At 400 degrees Celsius, it would be parallactic phase. Do you know the symmetry?
It's assumed to be monoclinic, P21 by C. But I mean, I don't know. So, not from our work, but others reported. You had a question?
Yeah, so I was curious as to whether or not you have any sort of in situ characterization during your PLD growth, and kind of, you have this changing of symmetry layer by layer. And
we have read, but we don't really see it because I think the lattice parameters are kind of similar.
Oh, but it's a big rotation, right?
Oh, when it rotates. Okay, so I didn't do the growth, so I should.
Okay.
That's a good question.
Might be interesting to see whether it's templating out as the tetragonal phase or if it's forming after the fact.
Yeah, that's a good question. Thank you.
Anything else? Okay, we'll have the next speaker come up.